In this section, we're just going to explain what an electrical transformer is. We already know that electrical power is the product of electrical potential, or the voltage, and the electrical current. We can swap those two things between each other using a device called a transformer, which is really just two coils of wire, and they're not electrically connected to each other, they're just in the vicinity of each other. And through one coil, you would have a high voltage, low current alternating current flow, and in the other coil, it would create the opposite of that. So a low voltage, high current flow from a high voltage, low current flow. This is the process of electromagnetic induction, where the presence of an alternating current flow induces a flow of current in a nearby conductor. And that's the way these contactless charging devices work. So a transformer basically swaps the values of voltage and current between the input side of the transformer and the output side of the transformer. Um, when current is high, why do we bother with those? Because current is a flow of electricity, and the higher the current, the greater the heating of the wire, and therefore the greater amount of energy is lost. So to transmit large amounts of electrical energy over long distances, it's better to have a small current and a high voltage. But to power our devices, we need a higher current. So once we get that electrical power to our house, we use a transformer to convert that to a lower voltage, 110 or 220 volts for our houses here in the United States, and a higher current, which is enough flow of electricity to power the electrical motors in our air conditioners and refrigerators. And you've all seen transformers. Here are some pictures of them at substations in this picture in the upper right. This sort of garbage can looking thing mounted to the ubiquitous power poles that we have around. That's a transformer. Inside that is just a whole bunch of coils of wire, and through one coil of wire is a high voltage, low current flow coming from an input source from a transmission power line, and that induces in the other coil a lower voltage, higher current flow, which then just gets wired to your house. And then the picture of the cell phone there, that shows that uh, the contactless charger just has this current sloshing back and forth in that pad, and that induces a current in the battery charging circuit in the phone. So that's what a transformer does, and the reason it's useful is to reduce power losses in transmission. So the electrical generating power plants will produce typically a high voltage uh, electrical potential. A transformer increases that voltage for the long distance power lines that carry that electrical energy across the countryside, and shown here it's 345 kilovolts. Then when it gets to a city, that gets reduced down to a more reasonable few kilovolts. And then the final step are these transformers that you see in neighborhoods that bring it down to 240 volts. And that's the potential that is brought into your house. And is most of that is split to 120 volt lines, which are most outlets. The 240, 220 to 240 are used for things like your electric dryer or your air conditioner. So you can check out, again, our additional resources here. And the other part of this part of the module has to do with the electrical grid. We've got electrical power plants wherever they may be. So nuclear power plants or fossil fuel burning power plants or windmills or giant solar arrays. And then we need to get that electricity distributed to everybody. And those different power plants, sometimes they need repairs. If it's wind, sometimes the wind isn't blowing. If it's solar, sometimes the weather prevents those from producing. So you have this fluctuating production of electrical power from all those different power plants, but you need a always available supply. So skipping to near the end of this section, this is a curve that shows how the demand for electrical power varies over the course of the day. And of course, it is lowest at night, but increases in the morning and peaks when people come home and in the evening when there's more lighting needed. And so you don't need a constant level of electricity all the time, but you need to be able to produce the amount that is demanded at all times, and you can't predict that perfectly. So having a grid that isn't able to send electricity uh, from many different power production sites to the different places that need it, and that are interconnected in a way such that if one part of a grid uh, loses its power production, you can get surplus energy from another part. And so a smart grid is required. But the flip side of that is that it means that power production plants need to be able to be producing more power than might be needed at any given time if you're going to guarantee that everybody's going to always have access to all the electricity that they need.